All right, this lesson is about the Maclaurin and Taylor series. That's what we're doing here. So, what this topic is really about taking a function, let's say f of x, and rewriting it as a polynomial. Now, remember that a polynomial consists of a constant, an x term, an x squared term, and so on. So, if you have, for example, f of x, our aim is to take f of x, which is going to be some function of x. It might be an exponential function, it might be a trig function, and so on. And we're going to take it and we're going to rewrite it as a polynomial. So a constant plus an x term plus an x squared term, and so on, right? And of course, this is a series because remember, a series consists of a sum of terms. So really, when you take your function and you convert it to a polynomial, then what you have is a series. So we're taking a function of x and rewriting it as either the Maclaurin series or the Taylor series. Let's talk about the Maclaurin at first. So when you take a function and you rewrite it using the Maclaurin series. So let's say, for example, I know that e to the x, if I write it in the as a Maclaurin series, it's going to be 1 plus x squared over 2 plus x cubed over 6. And you can see that the denominator is factorial. So this is 2 factorial, 3 factorial. This was over 1 factorial over 0 factorial. So we can take e to the x. I know this for a fact. E to the x can be written as this Maclaurin series. So what this is saying really, if we think in terms of, let's say, the graph of the functions, if we graph e to the x, and we graph 1 plus x squared over 2 plus x cubed over 6, what you're going to find is that the two functions are similar or equal at or around x equals 0. So the Maclaurin series is specifically for close to 0, around 0, about 0, right? So to the left, a little bit to the left of x equals 0 and a little bit to the right of x equals 0. So if I should sketch both of these functions, so the e to the x as well as this polynomial, if I should sketch them, what you're going to find is that close to x equals 0, around that area, the two functions are going to be equal. All right, and let me show you a graph of this. All right, so here is a graph showing the e to the x function, which is the red, and the polynomial, the 1 plus x squared over 2 plus x cubed over 6 and so on, is the blue one. That's the polynomial. And if you look at x equals 0 around this section here, then you'll see that the two functions are the same. You can't tell the difference. We're seeing the blue, the polynomial, on top of the red. We're not seeing the red. The red is underneath because the two functions are equal close to x equals 0. So at or around x equals 0. Now you can see that when you move away from x equals 0 to the left, maybe at around negative 1.75 here, you can see that the functions start differing. So the polynomial takes these values and e to the x takes these values. Same thing on this side of the 0. Maybe when you get to around a little past 1.75, you can see that the two functions start to differ, right? But at or around x equals 0, the two functions are equal. And that's what the Maclaurin series does for us. It takes a function of x and then rewrites it as a polynomial that is equal to our original function at or around x equals 0, right? Now, there are some common functions that are already, their Maclaurin series are already on the formula sheet that you're going to be getting. So this I took directly from your formula sheet. These are the functions that are provided, some common functions and their Maclaurin series. So for e to the x, the Maclaurin series is 1 plus x squared over 2 factorial plus dot dot dot, and then this shows us how each term is calculated. So x to the r over r factorial for all real values of x. So no matter what value of x we plug in, this is going to be the Maclaurin series. As you can see, if we want the third term, we'd plug in the r as 3. Well, it would be the fourth term, sorry, because this is the first term, second term, third term. So the fourth term, which is your x cubed term, we would plug in r as 3, and that would give us x cubed over 3 factorial. And we know 3 factorial is 6. And so on. The next term would have been x to the 4 over 4 factorial, and so on and so forth. So this is the Maclaurin series for e to the x. This is the Maclaurin series for ln of 1 plus x, and the x is restricted, right? This is the range for x that you're allowed to plug in. The Maclaurin series for ln of 1 minus x is also on the formula sheet. X again is restricted. The Maclaurin series for sin x is also provided. The Maclaurin series for cos x is also provided. These are the ones on your formula sheet. Now, what these allow you to do is, let's say I wanted to estimate the value of e to the 0.5. Let's say e to the 0.5, right? According to this, it would be equal to 1 plus, we're plugging in x as 0.5. So 1 plus 0.5 plus 0.5 squared over 2 factorial, and so on. It depends on how far CAPE requires us to go. But let's stop at the x squared term and see what we get. So this is going to be plugging into my calculator. I'm going to plug in 1 plus 0.5 plus 0.5 squared over 2, and I get 1.625. Let's check the actual value for e to the 0.5 now. 1.649. So you see, it's not exact, but it's pretty close. And if we should add more terms, it would get even closer, right? So it's not an exact value, it will be approximate. All right, good. Now, at the bottom, you will see this is the actual formula now for the Maclaurin series, to generate the Maclaurin series. So even if they had not given these to us, we could have generated them from this formula here. Now you'll notice that the formula involves derivatives. This is f prime, f double prime, f triple prime, and so on, right? So to generate the Maclaurin series for a function, you're going to need derivatives. You have to be able to differentiate. So the formula is f of x. So your function f of x is equal to f of 0. So you're plugging in 0 into the function, plus x over 1 factorial times the derivative of f with 0 plugged in, plus x squared over 2 factorial times the second derivative of f with 0 plugged in, and so on and so forth. You can see the pattern here. So you're taking a derivative with 0 plugged in, and then times x to the r over r factorial.